Hey limnologists, let's talk about lake stratification. We've already learned that lakes are really good at absorbing solar radiation. So what happens to all that accumulated heat? Well, let's find out. In this introductory video, we're going to cover 3 topics: lake stratification, density and resistance to mixing, and lake mixing regimes. You may notice a lot of unfamiliar terms in this video, and we've tried to underline those in blue. Most of them have Greek origins, and you should look them up to learn more. We're going to first examine thermal stratification through the lens of a typical temperate lake. It's good to remember that while temperate lakes are very abundant on Earth, there's lots of other types of lakes, and we're going to get to these later. Let's start by imagining a lake at the end of winter and the start of spring. The lake ice has just melted. It's still cool outside, and the lake is also cold. In fact, the lake temperature is 4 degrees Celsius throughout the entire water column. And this is the temperature of maximum density. When the entire lake is the same temperature, we call this isothermal. Iso is of Greek origin, meaning equal. On the right, you'll see a plot of temperature versus depth. These types of plots are very common, and you should become familiar with them, as we're going to use them throughout this video. Temperature is on the x-axis, and depth is on the y-axis. And in the spring, you can see that the temperature is the same at every depth. And because the temperature is equal, the density is equal, and that means the lake is relatively easy to mix. And, of course, we don't mix lakes with a spoon. Lakes are often mixed by wind energy. As time passes, the days start to get warmer, and the lake water absorbs light, which means the lake absorbs heat, and the surface waters begin to warm. As the surface water gets warmer, the density declines, which means the surface water is less dense, and the water at the bottom of the lake remains cold and dense. That density difference has caused the lake to become stratified, with warm water at the surface and cold, dense water at the bottom. As the days warm, that density difference becomes even more intensified. If we look at the temperature depth profiles on the right, what's interesting is that water temperature does not decrease linearly with depth. Instead, the top few meters all have the same water temperature. This is because wind uniformly mixes the upper portion of the lake. But there's not enough wind energy to overcome the density difference and mix the entire water column. Because lake stratification is so important for water chemistry and lake biology, we differentiate the water column into 3 separate zones: the epilimnion, or the surface water, the metalimnion, or the middle water, and the hypolimnion, or the bottom water. And in the summer, the epilimnion tends to be warm, and the hypolimnion tends to be cold. The metalimnion is the area that exhibits a sharp decrease in temperature and a sharp increase in density. The depth of maximum temperature change we refer to as the thermocline. The thermocline is calculated as the inflection point in the thermal profile. And so while the metalimnion covers a range of depths, the thermocline is found at one specific depth. And this is important because the thermocline is the depth at which we find the highest relative thermal resistance, or the amount of energy needed to mix water of 2 different water temperatures. On the right, you'll see a temperature profile from Lake Mendota, taken on July 9th, 2018. And you can see the epilimnion extends to about 6 meters depth, with relative uniform temperatures of about 25 degrees Celsius. Likewise, the hypolimnion is found between 12 meters and 25 meters depth, with water temperatures in the range of 8 to 10 degrees Celsius. In between is the metalimnion, where we see a temperature drop from 25 degrees Celsius to 10 degrees Celsius. This is also the area with the highest relative thermal resistance. We calculate relative thermal resistance as the density difference between 2 layers of water compared to the density difference between 2 layers of water at 4 and 5 degrees Celsius. In this profile, the highest relative thermal resistance is at 8 meters depth, which is equivalent to the depth of the thermocline. Because of that high thermal resistance, the thermocline acts as a barrier in the lake, and large amounts of energy are needed to break down the thermocline. It's also a barrier to transport of solutes, like nutrients, from the hypolimnion up into the epilimnion, and it slows the sinking of particles from the epilimnion down into the hypolimnion. Here's some data from a study led by Dr. Jen Klug in 2012, which show thermal profiles from 9 lakes located along the path of Tropical Cyclone Irene in 2011. Tropical cyclones have very high wind speeds, and while we can see that in some lakes, the cyclone did manage to break down the thermocline, it didn't happen in all lakes, which shows just how strong thermoclines can be. Another term you'll hear used when talking about lake stratification is turnover. So what is turnover? Well, we've seen that in the spring, a lake is isothermal, and in the summer, the lake stratifies into a warm epilimnion and a cold hypolimnion. This stratification lasts throughout summer, but in the fall, that warm epilimnion starts to cool down, and eventually it becomes cold enough that wind energy is able to mix the thermocline, and the lake once again becomes isothermal. These periods of full mixing, what we see in the spring and in the fall, we refer to these as lake turnover, because the entire water column is mixed. These turnover events are important for lake biology and water chemistry, because when the lake turns over, oxygen is replenished into the hypolimnion, and nutrients that have built up in the bottom of the lake are mixed into the surface water. We have yet to talk about what happens in winter, but just like summer stratification, lakes stratify in the winter, except they inversely stratify, with the coldest water on the top and the warmest water on the bottom. And this is due to the unique temperature-density relationship of water. After fall turnover, the lake uniformly cools down to 4 degrees Celsius, the temperature of maximum density. But as the surface of the lake starts to cool below 4 degrees Celsius, we start to see inverse stratification, with the epilimnion cooling to 0 degrees Celsius, and the hypolimnion staying closer to 4 degrees Celsius. Because the temperature difference can only ever be a maximum of 4 degrees Celsius, the thermocline in the winter has a much lower relative thermal resistance than thermoclines in the summer. So how do limnologists know when the lake is stratified? Well, we go out and measure water temperatures. Typically, we go out to the middle of the lake with a temperature sensor, which is just a sophisticated thermometer. And we measure the temperature at multiple depths and record these in a table. Then, when we get back to the lab, we plot up our familiar temperature depth profiles. Here's a video of how we collect temperature data. Let's take a temperature profile. I have with me a temperature logger, which consists of an instrument that has a readout of temperature, and a temperature sensor, which we're going to put into the lake. So let's get started. The temperature at 1 meter depth is 24.2 degrees Celsius. At 2 meters depth, it's 23.6 degrees Celsius. At 3 meters, it's 23.3 degrees Celsius. At 4 meters, it's 22.8 degrees Celsius. At 5 meters, it's 22.7 degrees Celsius. At 6 meters, it's 22.6 degrees Celsius. At 7 meters, it's 22.5 degrees Celsius. At 8 meters, it's 22.5 degrees Celsius. At 9 meters, it's 22.5 degrees Celsius. At 10 meters, it's 21.7 degrees Celsius. At 11 meters, it's 21.2 degrees Celsius. At 12 meters, it's 19.8 degrees Celsius. At 13 meters, it's 18 degrees Celsius. At 14 meters, it's 14.7 degrees Celsius. Now we're getting cold. At 15 meters, it's 12.2 degrees Celsius. At 16 meters, it's 10.5 degrees Celsius. At 17 meters, it's 9.8 degrees Celsius. At 18 meters, it's 9.2 degrees Celsius. At 19 meters, it's 8.9 degrees Celsius. And at 20 meters, it's 8.6 degrees Celsius. So we've gone down 20 meters in the lake, and we can see that the hypolimnion is pretty cold. I think that's far enough. 60 feet is pretty deep, and the hypolimnion is probably going to stay around the same temperature. And here we have it, a full temperature profile showing the epilimnion, metalimnion, and hypolimnion in the lake. So this is just collecting data on one day, in one spot. But to understand stratification, we need to take temperature profiles on multiple days. Here's a plot of dozens of temperature profiles taken on Lake Mendota over the course of 2018. We can see that in January, the lake is weakly inversely stratified, and the lake is isothermal by April. But by late May, the lake's begun to stratify, and stays strongly stratified throughout the summer, with a maximum thermocline depth at about 10 to 11 meters. Then, in late fall, the lake experiences fall turnover, and the water column is once again isothermal in November. But manually measuring lake temperatures repeatedly is a lot of work, and is often difficult depending on lake conditions. So instead, a lot of limnologists use high-frequency sensors mounted on buoys that record continuously throughout the year. These buoys provide a wealth of data that just wouldn't be possible to collect manually. So once we have a number of temperature depth profiles, we can plot temperature changes over time to see how the thermal regime is changing. And one way of doing that is by using isotherm diagrams, as seen here. These are very similar to a contour map you might use while you're hiking. These are made by plotting individual temperature measurements and connecting equal temperatures with a line. One way of reading them is by selecting a specific date and drawing a vertical line. If that vertical line doesn't cross any isotherms, then the lake is isothermal with the same temperature from top to bottom. If the lake crosses many lines, there's going to be a big change in temperature with depth, and many lines close together means a very sharp increase or decrease in temperature. This is usually associated with the thermocline. This is equivalent to a topographic map, where when you see many lines close together, you know that you're in for a steep incline. Often isotherm diagrams can be kind of difficult to read, especially when you have a lot of data. And now that we have more sophisticated graphing programs, we tend not to use isotherm diagrams, and instead plot lake temperatures as heat maps. This type of plot displays the same information, but instead of joining areas of equal temperatures with a line, we color areas of equal temperature with the same color. But they can be read the same way. If you look at a specific date and draw a vertical line, if there's multiple colors, you're passing through multiple temperatures. So in the summer, you can see that this lake is stratified. But in late November, the lake becomes isothermal. So when you read limnology papers, you might see lake temperature plotted either way. You could think of isotherms as the old school, original way of plotting lake temperatures, and heat maps as the relatively newer method. So now that we've learned about how lakes stratify, let's step back a minute and think about density and resistance to mixing. We've learned about relative thermal resistance, and that the highest relative thermal resistance occurs at the thermocline, where the temperature and density change is the greatest. We've also learned that the density of fresh water does not increase linearly with temperature. Instead, as water warms, the density differences become bigger. So the difference in density between water at 19 and 20 degrees Celsius is much larger than the density difference between water at 5 and 6 degrees Celsius. So that means warm lakes are more difficult to mix, because they have a higher density differential, whereas cool lakes are easier to mix because they have a lower density differential. So question for you. At which latitude is more energy required to mix epilimnetic and hypolimnetic waters? 38 degrees north or 48 degrees north? Why? There's actually two reasons. If you said 38 degrees north, you're correct. For one, lakes at more southern latitudes are going to be warmer, so they're going to need more energy to mix. They also tend to have a greater difference between their epilimnetic and hypolimnetic temperatures, and this degree differential is also going to make them harder to mix. Now we're going to switch gears and take what we learned about lake stratification in a temperate lake and think about lakes globally. So far, the seasonal pattern we've seen we can classify as a dimictic lake. This is a lake that mixes twice annually. It turns over in the spring and it turns over again in the fall. And dimictic lakes are very common in both temperate and northern latitudes. They're probably the most common type of lake on Earth if we ignore very shallow lakes. Here's a water temperature plot from Trout Lake in northern Wisconsin. It's a textbook example of a dimictic lake, where we have weak thermal stratification in winter. We have spring mixing and isothermal conditions, followed by summer stratification and a deepening of a thermocline, until we have fall turnover and mixing. Although this cycle is repeated annually, it does vary from year to year. So, question for you. In 2001, we had a cool and extremely windy spring. Would this cause the onset of stratification to be earlier or later than the average? And would the hypolimnetic temperatures be lower or higher than normal years? If you said later than usual, you're correct. Cold temperatures and wind are both effective at keeping a lake fully mixed, and so it would take longer for the lake to stratify. But because of this, there's more time for the hypolimnion to gain heat, and so often, during years of late stratification, the hypolimnetic temperatures are warmer than average. So now that we have learned all about dimictic lakes, what do you think might prevent a lake from being dimictic? Maybe you came up with one of the following. 1. It might be too cold. Maybe it never gets above 4 degrees Celsius. 2. Maybe it's too warm, and it never gets below 4 degrees Celsius. It never stratifies in the winter. A third option is maybe it's too shallow, and it mixes all the time. And another possibility is the density difference is just so strong, it never mixes. And we can classify all of these different regimes. So, in addition to dimictic lakes, which mix twice annually, we have monomictic lakes that only mix once per year. And these can be subdivided into cold monomictic lakes that don't stratify in the summer, and warm monomictic lakes that don't stratify in the winter. We also have polymictic lakes. These are lakes that mix frequently. And we have meromictic lakes that almost never mix. We can group the first 4 regimes as holomictic, lakes that mix at least once per year. And knowing the mixing regime can tell us a lot about how a lake functions. So let's look at these more closely. Cold monomictic lakes are lakes that mix once per year during the summer. They tend to be high latitude or high altitude lakes that are ice covered during most of the year, and they're weakly stratified under ice. When the ice melts in the summer, the lakes become isothermal, but never get warm enough to stratify. In contrast are warm monomictic lakes. These also only mix once per year. They tend to be located in climates that are too warm for ice covers to form, and so the water column stays mixed all winter. In the summer, these lakes stratify like a normal dimictic lake. In fact, with climate change, there's some concern that some dimictic lakes might become warm monomictic lakes in the future. Another mixing regime are polymictic lakes. These are lakes that mix frequently, and they're often shallow lakes that are easily mixed by wind. And because there's so many shallow lakes on Earth, there's lots of polymictic lakes. Lakes can also be polymictic if there's a lot of water moving through the lake. We say that the lake has a short water residence time. We can think of maybe a reservoir, where the water flushes through on the order of days to weeks. This high input of water can effectively mix the lake, creating a polymictic system. Here's a water temperature profile from Lake Wingra in 2018. You can see that this water temperature graph looks very different from the ones from the dimictic lakes earlier. Although Lake Wingra is inversely stratified under the lake ice in the winter, it's fully mixed the rest of the year. And this is because Lake Wingra is very shallow, only about 3 meters deep. We can attempt to generally classify lake mixing regimes based on latitude and altitude. Here's a classic schematic where we see that cold monomictic lakes tend to be at more northern latitudes, dimictic lakes tend to be at temperate latitudes, and warm monomictic lakes tend to be at tropical latitudes. And as we go up in altitude, we see more amictic lakes. These are lakes that don't mix because they might have a perennial ice cover. But remember, there's many exceptions to this general distribution. So far, we've only talked about density in relation to temperature, but we've noted earlier that salinity can also have a massive effect on density. In fact, the density difference between 4 and 5 degrees Celsius is the same as the density difference between just 0 and 10 milligrams per liter of salt, which is less than a tenth of a teaspoon of salt. Because of this, lakes with saline water will typically have stratification regimes that are controlled by salinity, not temperature. I've already introduced Monomictic lakes, as lakes that do not undergo complete circulation every year. Often these lakes have both freshwater and saltwater, and because freshwater has a lower density than saltwater, the freshwater acts as a cap above the bottom saline water. These two layers are separated by what we call the chemocline. This would be the area of the greatest density change in a Monomictic lake. Depending on the salinity of the water, the energy needed to mix across a chemocline can be incredibly large. Monomictic lakes can be formed naturally from a variety of processes, but they can also be formed by humans. One example is Little Round Lake in Ontario, Canada, where road salt runoff has accumulated in the lake, creating a saline bottom water. Another example is Mono Lake, California, which historically had been a monomictic lake, but freshwater diversions into the lake has caused some periods of meromixis. Just like how we've classified the epilimnion as the surface water and the hypolimnion as the bottom water in our thermal classification, we can classify the mixolimnion as the area above the chemocline that mixes, and the monomolimnion as the area below the chemocline that does not mix. Most limnologists call a lake meromictic if a chemically different bottom layer has been persistent for more than a year. And as higher concentrations of dissolved substances build up in the monomolimnion, the chemically different conditions are usually sustained because diffusion is very slow. But this doesn't mean the monomolimnion never receives new water. In fact, many meromictic lakes have periods of episodic deep water renewal, and this has been well studied in very deep lakes like Lake Baikal or Lake Malawi, where you might have intense cooling at one end of the lake or a big windstorm, where pockets of water from the mixolimnion are entrained down into the monomolimnion. One fascinating outcome of saline density effects is inverse thermal stratification due to salinity. This is when the salt water at the bottom of a lake can actually be warmer than the surface water. Here's an example from Lake Vanda in Antarctica. This lake is about 75 meters deep and also has exceptionally clear ice, which you can see in this photo. The result of that clarity is that solar radiation is able to penetrate deeply into the water column and warm the monomolimnion. And the result is that the bottom of this lake is about 21 degrees Celsius. And that's insane given that the average air temperature of this region is about minus 20 degrees Celsius. So to wrap things up, you should know that we have lots of terms for stratification, including the thermocline, which is the layer where we see the maximum change in temperature. Also the halocline, which is where we see the maximum change in salinity. The chemocline, which is the maximum change in chemistry. And generally, these are all referred to as a pycnocline, where we see the maximum change in density. And remember that, like everything in life, lakes are continually changing, and they don't necessarily show the same pattern every year. For instance, a dimictic lake, which does not freeze in a particularly warm winter, might experience a monomictic year. Likewise, a usually monomictic lake may have a dimictic year in a particularly cold winter. Or an extreme storm event may destroy a monomolimnion in a meromictic lake. There's lots of examples of lakes that have changed because of human influence. For instance, after dropping the water level, the Dead Sea has been holomictic since 1979. And we already saw the case study of Mono Lake, which turned meromictic for several years after reconnecting freshwater inflows into the lake. And as we'll learn later, stratification has huge ramifications for oxygen and nutrient dynamics in lakes. So now we've seen how climate influences the thermal characteristics of lakes and how lakes stratify. And soon we'll learn how stratification then influences water chemistry and also lake habitat.